correspondence, one needs to consider objects in derived algebraic geometry. So, for instance, the stack of local systems was naturally a derived object. So even more reason to consider derived algebraic geometry in this story is that while the stack of local systems is not, there are ways around it being derived. For instance, you can consider curves of semi-simple groups and curves of genus greater than 2 and so on. The intermediate steps involve derived algebraic geometry in an essential way. So I wanted to start by saying something a little bit about what derived algebraic geometry is all about and how it's a general, well, and we'll see. So, but before that, let's say what algebraic geometry is all about, regular algebraic geometry. Well, probably if you look on Wikipedia, unfortunately I haven't tried this, it'll tell you something like that algebraic geometry is the geometry of solutions of polynomial equations. You have some polynomial equations, they define a variety, so that's all very good, but this has a number of problems, and there are kind of two approaches to formalizing this. So the formalism, so one is as schemes. So to any ring, you can assign its spectrum, which is a topological space with its Zariski topology, and it naturally has a sheaf of rings. So it's a kind of a locally ringed space. So that's the approach probably people usually take. But there's also another approach, which is equally important, which will be a little bit easier to generalize to the derived world, which is the functor of points. So if I have a variety, this gives I can think of it as a functor from rings to sets, namely, well, rings will always be commutative rings. To a ring R, I assign the set of R points of X. So, well, if you think about it, this is actually a little bit closer to the idea that varieties are solutions of polynomial equations because, well, when you say solutions of polynomial equations, you can ask, well, in which space do the solutions lie? And the answer is this ring R, and you can study how this set of solution changes as you vary different R. And this functoriality and this sort of thing knows everything about the variety you started with, essentially by Yoneda's lemma. So fundamentally, we'll say that algebraic geometry is about functors, let's say from rings to sets. So, of course, not every such functor is given by an algebraic variety, but nevertheless, it gives a natural generalization. We can just try to study this functor and see what kind of geometric properties we can extract from it. So, well, derived algebraic geometry now. Now it's really easy to say what derived algebraic geometry is about. It's about studying functors from derived rings to derived sets. Of course, just adding the word derived doesn't do anything. So I have to tell you what. So I have to say what derived rings are. I have to say what derived sets are, and indeed, I have to also say what a functor between such things is. So the problem you run into is that, or maybe not a problem, maybe a feature, depending on your point of view, is that these things are not, unlike these guys, these things are not ordinary categories. They're now infinity categories. So both left-hand side and right-hand side are infinity categories. So from now on in the rest of the talk, I'll drop this prefix infinity, and categories will always be infinity categories, functors will always be functors of infinity categories, and so on. Anyway, so first let me say what derived sets are. That's a funny way of saying, well, it's what is sometimes called the category of spaces. So one kind of relatively concrete way of it is if you think about Conn complexes, so simplicial sets, which are Conn. Another name for it that we've already seen is infinity groupoids. So I think Sam explained that you can think of a topological space or a simplicial set if you take its fundamental groupoid, then that's an infinity groupoid, naturally. And there's in fact some kind of equivalence of homotopy theories of infinity groupoids and topological spaces or simplicial sets. So this will be our basic thing. And now derived rings. So there are different versions. Luckily, we're working over characteristic 0. So first of all, we'll work over a fixed field of characteristic 0. Outside of characteristic 0, things are a little more subtle, but in characteristic 0, we can take derived rings. These will be the same as commutative differential graded algebras in non-positive degrees. So these are connective CDGAs. All right. So and then a functor will be a functor of infinity category. So I guess definition, a prestack. This is just a functor from I don't know, derived rings. Let me say infinity groupoid. So we've already seen this. What's that? No, functor between infinity categories. So as I said earlier, all categories, unless stated otherwise, will be infinity categories, and all functors will be functors of infinity categories. So I don't want to get too much into what this means. It's perfectly fine to. These behave in many ways just like functors. So many of the usual words you say still make sense. And so, well, if you know how to do one of these things, then you'll know. Oh, if I said affine schemes, then it would be from the opposite category. Yes. So this is the same thing as, maybe let me call it DG schemes affine. Affine opposite. So yeah, so this is what.
There's no relationship between the use of the term derived for rings and for sets, right? Is there? I mean, they look like completely different.
Well, philosophically, they're similar kind of things. So, and in fact, they are the same because, well, a ring is a set with some operations. A derived ring is a derived set with some operations. I gave you kind of a more explicit definition, but you can define a derived ring in this way. Oh. So indeed, it's more than just an analogy.
So the degrees
and then it will agree with this.
The degrees
What's that?
What's the underlying set for derived ring?
So there's something called the Dold-Conn correspondence, which gives an equivalence between simplicial sets and chain complexes corresponding in non-positive degrees. And the underlying set is, think of this as a chain complex and apply the Dold-Conn functor. So that will be the underlying set. As I said, this equivalence is not completely trivial, but it's true. Okay.
So when you write the right rings, you take the category of all DGs and invert what is.
Yes. Yeah, that's right. So I told you what the objects are, and these are up to quasi-isomorphism, and this forms an infinity category. So I think infinity categories really are a prerequisite for this. So I don't want to say much more about that. Well, as was pointed out, so why is such a thing a good idea? So first of all, as Dennis already pointed out, whenever you have a moduli problem, it's a good idea to try to formulate it as a derived moduli problem. So a derived moduli problem would be the same as a prestack, because it gives more structure. So one advantage of derived algebraic geometry is that you can actually, if you have such a functor, you can extract more information about the underlying kind of geometry of the thing. For instance, the cotangent complex is something that you can extract directly from this functor, which is not true in usual algebraic geometry. Also, kind of more concretely, returning to the question of how you would know that local systems should be a derived stack rather than an ordinary stack. Well, one way to, so it's more of an art than a science of promoting classical non-derived things to derived things. But in the case of local systems, you can arrive at this by thinking about what deformations of local systems should look like. So if you form the naive stack of local systems, you'll find that it doesn't have the deformation theory you expect the local systems to have. And this, thinking carefully about it, will lead naturally to the derived moduli problem. All right, so, but before I continue, let me give one example, which is affine derived affine schemes, which is if I have a derived ring, I can associate to it the spectrum of A, and this is and as a functor, this evaluated on B is the mapping space in derived rings from A to B. So it's the same formula as you would define spec of a ring. Now, the difference is because derived rings form an infinity category, maps between them form a space. So again, in this particular model, this involves some version of the Dalt-Kahn correspondence to arrive at this. But let me not get into that. So these are going to be the basic objects of study. I guess before moving on, let me say that there's another approach to trying to do this, which is not the functor of points, which is, again, you can say, well, is there some version of this spectrum of a ring? And indeed there is. So there's also a version using locally ringed spaces so very briefly, if I have a DGA, I can define the topological space to be just the spectrum of H0 of A. So it's going to be the same topological space as the ordinary Zariski spectrum of the zeroth cohomology, but now it's going to have a different sheaf of rings, so with different so now, well, it's going to be a sheaf in some infinity sense, and it's going to be a sheaf of differential graded algebras rather than a sheaf of rings. But, well, I guess you'll have to believe me that localization works for these kinds of things. But, well, one reason to bring this up is I want to point out, first of all, that the Zariski topology makes sense in the derived world. And second of all, from this definition, this suggests a philosophical point, which is a useful one, which is that you should think of derived schemes as some kind of generalized nil thickenings of ordinary schemes. So in the same way that if, well, the difference between scheme theory and the theory of varieties is that you allow yourself to consider rings with nilpotent elements. And if you think about what the spectrum of a ring with nilpotent elements is, the underlying topological space is the same thing as the spectrum of the reduced ring, with just a slightly different sheaf of rings. So this works the same way. And so somehow you should think of elements of lower cohomology groups as some kind of generalized nilpotent elements. So this turns out to be a very fruitful viewpoint.
And can you define some non-affine derived schemes as that way?
Yeah, by gluing, yes. That's right. Exactly.
is this approach particularly useful?
Yes, yes. As in regular algebraic geometry, both approaches give useful. I mean, you can do.
Well, something that you can easily do here, but can't do with functor of points.
Well, I mean, you can always do everything with functor of points that you can do with.
But
Some things become more conceptually easier in one point of view.
This gives some restriction, right, on which functors the points are allowed.
For instance, yes. But, well, an exercise that is worth doing in regular algebraic geometry is to characterize schemes among various functors from rings to sets. So, you could write down what it means to have a cover by affines in that world. So that's not. I'm sorry? Oh, so the reason you need characteristic 0 is because commutative differential graded algebras is not a concept that's well behaved in characteristic P or over Z. There are lots of problems. So if I remove the word commutative, there would be no problem. But for commutative differential graded algebras are not a good thing to consider in general.
Nil contents living in different degrees being made precise.
Yes, but let me not, well, I'll say a little bit more about that later. So, okay, great. So moving on, so the goal of this talk is really to define Dmodules on such objects. But first I need to say something about quasi-coherent sheaves. But even before I can do that, I should say what kind of things quasi-coherent what kind of thing that quasi-coherent sheaves will be. So the first goal will be that if X is a prestack associated to it a DG category, which we'll call quasi-coherent sheaves on X. So, well, let me at least set up some notation and recall about DG categories. So there are various ways of formalizing these ideas, but I don't want to really get into any of them, but just sort of mechanically what sort of operations exist is, well, you have some objects. I don't know, so say C is a DG category. So the thing that you can do is that if you have two objects, C1, C2, you can consider what I'll call curly maps, C1, C2. So this lives in the category of vector spaces over K. And vector spaces, again, by default, everything is derived. So vector spaces will mean the DG category of chain complexes over K. So you can associate one of these. Oh, but the point is, you can think of as a DG category as a kind of infinity category. So infinity category is something that has objects and mapping spaces between them. So how do you associate something like this? So you can define maps, no curly, maps from C1 to C2 as a space. You look at the truncation of this chain complex. And, well, if you want to get a space, you apply the Dolcon functor to it. So this is a space via Dolcon. So in particular, it's an infinity category, and you can, well, it's something that's called a stable infinity category, whatever that means. But the point I want to emphasize is that these guys actually know so it might look like you truncated, so you lost some information, but in fact you haven't. You can, if it's at least pre-triangulated, which everything is going to be, DG category for me will always be pre-triangulated, and so you can use the triangulated structure to recover the entire mapping space, not just its connective cover. So that's what a DG category is. So a functor so by a functor, well, there's a usual problem with defining what a functor between DG categories is. So let me say, well, as I tried to explain, a DG category has an underlying infinity category. So a functor will be a functor of infinity categories. Which is exact. So exact means, well, there's a notion of an exact triangle. So sends exact triangles to exact triangles. That's one way of saying it. And another way of saying it, slightly more abstractly, but equivalently, is that it preserves finite colimits.
Is it the same as a DG functor or not?
Well, I don't know what you mean by a DG functor.
Just a functor which says that the map between chromes is a map of chromes.
No, it's not the same thing, because you need to resolve in general.
I need what?
Oh,
Quasi-equivalence, like strict DG functors in the sense that you said, do not have a quasi-inverse, right? So
yeah. So this is like DG functors up to quasi-equivalence. So you. So one way of making that explicit is by looking at various kinds of resolutions, or well, there are a number of ways of making this explicit, but I don't want to get into that. So what's that? Oh yes, thank you. Thank you. Yeah. So
Stable.
what's that?
You want to emphasize the stable, otherwise exact triangles are not so defined.
No, they're defined. It's just a cofiber. No problem.
Not easily you need zero.
It's anyway. There is a notion in such things of exact triangles, because they're stable. I don't want to get into the specifics of what that means. I think that would not be so helpful. So that's what a DG category is and what a functor between these is. So usually we will consider not just DG categories, but DG categories which are, so unless stated otherwise, so DG categories have all small colimits and functors have to preserve all colimits. So that's a kind of, both of these are kind of additional restrictions. We'll see a little bit later. Let's just take that as a black box for now. I think in the tutorial we'll see why that's a good idea. All right. So anyway, I think this is all I wanted to. Yeah.
That K is maybe unbounded.
Yeah. Unbounded. Unbounded, infinite dimensional, anything. All right. So now I'm ready to say what. I'm sorry?
That was a joke.
Oh, no, not small. It is not, in fact, a small category. So quasi-coherent sheaves. So, well, what do we want these things to be? Well, the starting point is that we're building everything out of affines. And so if A is a derived ring, we'll define quasi-coherent sheaves on the spectrum of A to be just the DG category of A modules. So, well, you can look at chain complexes with an action of A. There's a notion of quasi-isomorphism. Invert that, this forms a DG category. But now let's try to glue these all together. This is sort of the first place where it's really essential that we're using DG enhancements rather than triangulated categories, is that these operations give sensible answers. Well, so suppose we have a map of rings. B. Derived rings. Then, well, tautologically, we have a restriction functor from B modules to A modules, right? If you have a module over B, you can think of it as a module over A, no problem. So this has a left adjoint let's call it F upper star from A modules to B modules. And this is exactly what you think it is. If I have a module M, it sends it to M tensor over A with B. One caveat is that this is the derived tensor product. So if I wasn't suppressing all these derived symbols, I would put an L here. But everything is derived. Okay, great. So, yeah. So we have these two functors, and we have some additional structure on these categories. So if I just have A mod, well, we've already seen there's some kind of an operation of tensoring over A. So this is actually a symmetric monoidal category. So the symmetric monoidal structure is tensoring over A. Is there a question?
There is also a sense that, so it's not about the derived category of the DG category, right? Of A models. You just.
What do you mean? It's just on the DG categories.
Yes. I mean, there is a derived tensor product in the sense that you pass to the derived category of the DG category.
No. This is not what I'm talking about. This is in the. So I haven't defined what this means. One way of defining it, which I'm sure you will not find satisfactory, is formally as the left adjoint of this functor. For formal reasons, it exists. But
Can you be more precise? Is A mod the whole homotopy category of A of the category of DG modules, or is it the model for the derived?
it's a model for the derived category. It's a DG enhancement of the derived category. So there are various ways to construct it, of course, and I don't want to pick one. Yeah. So its homotopy category is not the homotopy category of A modules, but the derived category.
Is bounded below or?
No, unbounded. Everything. Yes. That's right. Yeah, it's also a bad conflicting terminology, but don't blame me. So yeah, so this has a symmetric monoidal structure, and with respect to this symmetric monoidal structure, so more or less tautologically, this F upper star is a symmetric monoidal functor. And F lower star, well, let's see what F lower star is. F lower star, of course, is not a symmetric monoidal functor. But because F upper star is a symmetric monoidal functor, well, there's a symmetric monoidal functor from A modules to B modules. That means we can regard B modules as a module category over A modules. And F lower star exactly preserves this structure. So this is a functor of A mod module categories. So that's a pretty abstract way of saying something very specific, which is that it satisfies the projection formula. So i.e., we have.
But according to your convention, this is not a functor because it doesn't preserve coordinates.
Oh, no, it does preserve colimits.
Oh, yes.
We have maybe the projection formula. So in other words, that if I take f lower star of m tensor f upper star of n, this is the same thing as f lower star tensored over b tensored over a of n. So this is explicitly, well, this is some down-to-earth version of what it means for f lower star to be a functor of a module categories, because, well, the action of this is you pull back in tensor here. Question? I see confused looks.
So you mean it's symmetric because it's commuted in geometry?
Yes, absolutely. Otherwise, well, if it wasn't commutative, there wouldn't be a tensor product that's internal to this category. You can tensor left A modules and right A modules and get a vector space. All right. So this is what happens for affine schemes. So now let's try to glue this in some way. So well, again, suppose X is a prestack. So we can take as the definition the category of quasi-coherent sheaves on X. As Dennis already wrote this formula. So this is affine DG S mapping to So it's this formal limit. Well, what is it in more down-to-earth terms? It is roughly the following kind of data. So what does it mean to give an object of quasi-coherent sheaves on X? What this means is the data of, well, suppose we have a map from spec A to X. So in other words, by definition, that's just a point in X of A. Then to this, for every such map, we're supposed to assign something we'll call f upper star, which is an A module. So that's the first piece of data. Second piece of data is that if we have a map from spec B to spec A, let's call it G, and let's call, so this gives them composed map, a composite map from spec B to X, which is F circ G. So we're supposed to give an isomorphism between, well, so we can take the module associated to this composite map. That's one thing we can do. Another thing we can do is we can take the pullback of the module associated to F, and this is we're supposed to give this as an isomorphism of B modules. So we're not done because there's some coherence for further composition. Even at the abelian level, there would be a co-cycle condition, but in this world of infinity categories, this is infinitely many. So plus
is it
coherence.
Through a model or through
No, an object. So this guy is an object of this DG category.
what's the DG category?
Yeah. So whenever I write this symbol, this means object of. If you like a functor, a DG functor from the point category to this guy. So this is roughly the data of what a quasi-coherent sheaf is. But now, so let's see how to work with such things. Or, well, first, in order to work with such things, we'll first need some more formal properties. So first of all, I'll observe that for tautological reasons, if I plug in an affine scheme A here into this formula, I will get back what I expect, which is if I plug in fx as spec A, then this really just recovers back A modules. So this is, don't want to get into this, but for completely formal reasons, because we can what is final in this category is where we take this to be the identity map. So this is some standard yoga about in category theory. But now, suppose we have a map of prestacks from x to y. So then I claim, just from the construction, there's a functor f upper star from quasi-coherent sheaves on y to quasi-coherent sheaves on x. Well, and so let's give a rough definition of this functor. Well, what does it mean? So suppose I have an object which is a quasi-coherent sheaf on y. I want to assign to it a quasi-coherent sheaf on x. What does that mean? That means for every spec A mapping to x, I'm supposed to give an A module. Let's call this F. Oh, whoa. Let's call this G. But x, remember, maps to y. So I assign to, so I define G upper star of M as well. Well, whoops. I define G, so whatever F upper star of M is, I have to define what G upper star is for every affine map. And well, hopefully the notation is suggestive enough that it's just, I take the composite and it's whatever was assigned to this composite map, which makes sense because it's part of the data of what a quasi-coherent sheaf on y is. So, well, I've only defined it for every map, but it's sort of easy to believe, at least, that this kind of assignment satisfies all the coherence conditions, just because it did for y.
Sorry, just for the definition of protocol, do you mean actually that you have to provide all some much more data, some compatibility?
That's right.
For going to infinity?
That's correct, yes. So far, this is not a very workable definition. So this is not something you can write down explicitly. On the other hand, if you've written down one of these, you know how to pull it back, because you just pull back all of this infinity amount of data. So far, I'm just describing some formal operations, and then we'll see how to use these formal operations to describe this category much more explicitly. So as Dennis mentioned, the definitions are very abstract, but at the end of the day, it's not so hard to compute. So there is such a functor. So now, I guess the other thing I should say is that, sort of entirely for formal reasons, this guy is a symmetric monoidal category as well. Sort of for each affine, separately just tensor the two modules. And this also gives a coherent association. And for the same reason, F upper star is a functor, is a symmetric monoidal functor. Okay. Now, so as we said, functors, by definition, are ones that preserve colimits. And, well, by construction, this functor preserves colimits. So by the adjoint functor theorem, there exists a right adjoint let's call this f lower star. So there exists some right adjoint, but for instance, it need not be continuous. So there's nothing that guarantees that this right adjoint preserves colimits. And in general, it does not. So in general, this kind of right adjoint push-forward functor is very badly behaved, and in particular, it's not the kind of functor we want to consider. All the functors we want to consider are continuous ones. No. This is completely formal, because this is a functor between presentable categories which preserves colimits. Such a functor always, accessible functor between presentable categories which preserves colimits, such a functor always has a right adjoint. Well, I didn't, so I have to say more careful, x and y have to be accessible. But let me ignore any issue. These are issues of set theory, so let's not worry about these things, because they never really come up. All right. So, but there is a well-defined push forward in some cases. So, but if the functor from x to y is schematic, then f lower star is well behaved. Yes, in particular, it's continuous. And oh yeah, I'm about to say. So in fact, i.e. continuous satisfies base change and projection formula. All of these things are false in general. So schematic you define this adjective. So, which it means that if we take a pullback with respect to any, let's say, affine scheme, TG scheme, then this is a DG scheme or derived scheme. So I didn't give a precise definition of what a general derived scheme is, but it's something that's Zariski locally an affine scheme. So this you build it in roughly the same way as you build schemes out of affine schemes.
So also conditional non-positivity of grading.
Yes, for instance. Yeah. So let me say why that is. So in fact, in this case, we can give an explicit formula for what this right adjoint is. So what we can say, so what is star in this case?
Sorry, what does satisfy base change mean?
I'll say that in a minute. So suppose we have a map from x to y, and we have something mapping to x. Well, in particular, So f. So suppose M is a quasi-coherent sheaf on X, and we want to define to evaluate. Let's call this G upper star of F lower star of M. Right? This is the kind of data that I need to define a quasi-coherent sheaf Y. So for every affine mapping to Y, I need to evaluate this in a coherent way. So what I can do is I can take the fiber product, what do I call it, S prime, here, G prime, F prime, and then I define to be, well, the thing from base change. So first you do G prime upper star, and then I do F prime lower star. And note, now both of these operations make sense. So pullback I can always do, and this guy is schematic, so, well, push forward is a local thing. I can just compute it via, let's say, check resolution of an affine cover here. So this makes this functor makes sense and is well behaved. Right. So let's stick to this.
Why G prime inverse image makes sense?
Inverse image makes sense for anything.
I mean, it's not in a file digit scheme, it's just a digit scheme.
Sure, but what is? I said before that for any map of prestacks whatsoever.
It's a limit anyway, so, right?
No. Look, for any map of prestacks whatsoever, inverse image on quasi-coherent sheaves makes sense. And this is an instance of that. I mean, if you like, if you have an affine here, further pull back.
That was commuting with the co-limits.
Yeah. Oh, ooh, whoops.
You said before it need not be, it's a functor, but need not
Yeah,
be
that's right.
So usually you were assuming all functors be continuous, but
Yeah.
then you were saying this one is a.
This one doesn't live in that world.
And what was the adjoint functor theorem? What version of adjoint functor theorem are you appealing to?
Just the adjoint functor theorem for infinity categories.
So somewhere in here you need to implicitly check that F upper star is a sheaf.
Yes.
You use this when you're on this board here.
That's right. So I needed that it's a sheaf in the Zariski topology. In fact, it's a sheaf in the flat topology. Yes?
Why S prime is continuous?
Why this guy?
Yeah.
Because it's a map of well. So if both of these were affine, this we knew from before that this was continuous. Now,
Do you need some
I need.
finiteness of covering or something?
No, I don't need that. What I need is that. Oh, I'm sorry. Oh, I'm sorry. Yes, thank you. So I would like to assume. I need more assumptions that this is quasi-compact and quasi-separated. Yes, thank you. Is there some more chalk? Okay, great.
Is there a partial converse or a converse to the statement that if F lower star exists, then you know what properties the morphism possesses?
No, not really. I don't know. So this kind of statement is true in more generality than schematic. For instance, you can replace schematic by something called representable, which means that the fibers are not schemes, but some version of algebraic spaces. That's still true, and well, it's true even in more generality than that in some examples, but I don't know any general statement that's a converse to this. So, all right. Okay. Yeah, so we have this, so we have these functors. Yeah, so let me formulate what base change means, as I promised. So base change means the following. So suppose I have a map from X to Y. And suppose this map over here is schematic. So let me give these names. f prime g1, g2, and suppose that, so this is a Cartesian, this is a pullback square. And f is schematic. By the way, this automatically implies that f prime is also schematic because, well, it's easy to see from the definition that it's stable under base change. So, yeah. Yes, thank you. And also that's a property that's stable under base change. So then we have that if M is a sheaf on X, then there's an isomorphism. Let's see. So we do G2 upper star, F prime lower star, and then F lower star, G1 upper star. So there's an isomorphism like this. So I want to emphasize that in this case, because the upper star and lower star functors are adjoint, this isomorphism is not additional data, but it's a condition, because there's a natural transformation between these two just coming from the adjunction. So this is just a property. So anyway, I guess one upshot is that we have a functor from the opposite category of so let's call it quasi-Coherent upper star, from the opposite category of prestacks to the category of DG categories and continuous functors, whatever that means. All right. Great. Upper star means that, well, it's saying what it does on morphisms. So to a morphism, you just pull back with upper star. All right. So, oh boy, I think I have 5 minutes remaining for this talk. So let me get to in the last 5 minutes, let me start at least. Well, let me start telling you about Dmodules now. So that was really all warm-up for Dmodules. Okay, so let's go back to differential geometry for a second. So, a problem. Okay, well, anyhow, so a problem that Dennis pointed out was that the formula that you might write for what a flat connection is doesn't really, it's hard, at least hard to do. A priori doesn't make sense in this derived world. So we have to do something else. So formula for connection doesn't make sense. So we need a different idea, and the different idea is that the data of a flat connection gives, on a vector bundle, gives an identification of fibers at infinitesimally closed points. in other words, well, if I have a map, so this is sort of the algebra geometric version of parallel transport. So let me try to, for lack of time, let me just give the formal definition and then unwind it to see that it recovers something reasonable. So the idea is this. So we want somehow the data of a sheaf, let's say on a variety or a prestack or whatever, which is identified at infinitesimally closed points. So what we can try to do is quotient out by this equivalence relation where we identify infinitesimally closed points. And then if somehow we succeeded in doing this, then Dmodules would just be quasi-coherent sheaves on that quotient. So rather than going through this whole procedure, let me tell you what the answer for this quotient is. So let X be a prestack. So definition, the Rham prestack of X, let's call it X Rham, is defined as, well, so I need to say what X Rham of a ring is. So by definition, I just take X, I take H, I don't know, R, let's call this A, I take H0 of A, and then I take the reduced part. So by this I mean quotient by the nil radical. And then Dmodules on X. Well, another name for this will be crystals on X. This will be defined as quasi-coherent sheaves on X Rham. So one thing to note is that this category doesn't actually depend on the derived structure of X. So suppose that X was an affine derived scheme. When we plug this in, this value only depends on A. So if X is spec A, X Rham only depends on the reduced part. Oh, let me say spec B. On the reduced part of H0. So, well, in the theory of Dmodules, there's Cauchy-Juarez's lemma, which says that if you have a nil thickening, this induces an equivalence on the categories of Dmodules. So this immediately gives a version of this, incorporating this idea that higher or elements of negative cohomological degree are analogous to nilpotent elements, because we quotiented out by them the same way. So there's that. And so sort of formally given a map of prestacks from X to Y, there is a pullback functor so let me call it f dagger L from, what's that? Dagger. From well, Dmodules on Y to Dmodules on X. So this notation, why the reason for this notation I'll explain in the tutorial, but this is just the pullback functor and quasi-coherent sheaves for the Rham stack. Now, in the remaining -2 minutes, let me try to explain why this indeed has something to do with Dmodules. So suppose suppose X is a smooth variety, is an ordinary smooth variety. Well, we have a natural projection map from X to X to Rham. And so we can try to study, well, we can try to study sheaves on X to Rham via sheaves on X. So the way to do that is to take what's called the check nerve of this map. In other words, form the simplicial scheme, which is iterated fiber products here. So let's see what the fiber product is. So note, if we take the fiber product of X with itself over X to Rham, I claim this is going to be the formal completion of the square of X along the diagonal. So in fact, these assumptions about ordinary smooth and variety are completely irrelevant. This will always be true, although I guess then you have to wonder what formal completion means. And so this check nerve is just given by what's called the infinitesimal groupoid. So we have various powers of X, and to take formally completed along the diagonal, and then we're studying sort of sheaves on this. So in our case, X to Rham as a prestack is isomorphic to the colimit of this simplicial prestack. And well, from the definition of quasi-coherent sheaves, it formally follows that it takes colimits of prestacks to limits of categories. So in other words, quasi-coherent sheaves on X to Rham, this is the same thing as a limit of quasi-coherent sheaves of X and this formally completed guy. Well, X is a smooth scheme, so we know a lot about these things. These are just regular derived categories of quasi-coherent sheaves. So we can study this as a derived category of some abelian category. So if we look at what the corresponding abelian category is, the heart of this thing, this will be the derived category of the corresponding abelian category. Well, we'll see these are exactly quasi-coherent sheaves equivariant with respect to this groupoid. Now, what does that mean? Well, remember, there's Grothendieck's definition of differential operators, which are distributions supported on the diagonal. And so from this, you could readily see that being equivariant with respect to this groupoid is exactly the same as being a module over the ring of differential operators. So indeed, at least in that case, it recovers the usual notion of Dmodules. In general, this category is not the same as modules over the ring of differential operators, but a much better behaved version of it. So I think I'll stop here for now.